Welcome back. And with this lecture, we officially start part two of the course, which focuses on the concept of fields. And so this is really the part of the course that is responsible for the name of this very course, Statistical Theory. And this is partly due to the fact that in the early version of the course, I was giving more emphasis on this part of the course, introducing more subjects to it and more applications. There are many reasons why this part of the course has shrinked considerably over the years. Not last the fact that some of the topics that I discussed in the first part of the course are quite hot topics in science today. So, according to my personal judgment, uh, for those who are interested in pursuing a career in the future, those will be scientific career in the future. Those will be more strategic. It's sort of important and strategic to know. I wouldn't say more strategic because there are interesting topics in any fields of science. What I'm trying to say is that I decided to give tools into developments that are very rapidly growing these years. Nevertheless, fields are here to stay, meaning field theories are essential tools for a variety of problems, not only in the context of relativistic quantum mechanics, where they are unavoidable tools. Those of you who have taken quantum field theory, they know that there is no way you can make a formulation of quantum mechanics that is consistent with the notion of relativistic causality without invoking fields and antiparticles in general. And this is very clear. There's a prologue chapter in, say, Pesky and Schroeder books that really explains why is that. You can, however, make a version of quantum mechanics that is relativistic covariant, so that you have a covariant transformation of the Schrödinger equation, but you won't be satisfying at quantum level the constraint of causality, meaning that commutators between operators that are separated by space-like distances should be always zero. So if you're interested in relativistic quantum mechanics, then of course fields are mandatory. There's no way out. But when you discuss either non-relativistic systems or even classical statistical mechanical systems, fields are an option you choose to adopt to effectively model a physical system. So to give an example, let's take a very sort of intuitive example of fields. Suppose we want to study the motion of particles in a pipe. Maybe this is precisely the pipe we use to wash our hands in the morning in the bathroom. So these are little molecules of water. They have a little bit of a velocity scatter along the y-axis, but mostly they are pointed along the x-axis if the water is flowing this way. Well, actually, you can orient this in any direction you want. Well, if you want to study this process, you have always an option, which is that of performing. Suppose you're not interested in simulating the entire pipe. Maybe you're interested in a portion of the pipe. And it makes sense to wonder whether you should use a particle description in which you simulate the dynamics of all these particles, say by integrating the equations of motion with the same techniques that I sort of glanced through in the first part of the talk. Or if it makes more sense to introduce, say, a density and velocity field in the pipe, which describes Maybe this is a velocity field in the pipe, which basically corresponds to conceptually dividing my pipe. Oh, sorry, I'm having some problem. Okay, conceptually dividing my pipe in a grid and assign to each point an average velocity. Right? Now, from the conceptual point of view, if this is a statistical system, all you can actually care of are distributions. So I think it's clear there is no real more information in a trajectory than there is in average distribution of, say, velocity and fields. It looks like there is more information because you have the position and velocity of each particle. But you have to average over an ensemble of such independent configurations, a result of which all it really matters is the average probability of having a given velocity and density locally. Because all this really microscopic information used to solve the dynamics can only be considered as a tool to sample those distributions, because in a statistical sense, the only thing that matters is the distribution. So for the point of view of fundamental information you get in defining an equation for the, say, velocity fields, Boltzmann-like equation for the velocity fields, lattice-Boltzmann sort of approach, or a velocity field, meaning the average velocity in each point in space, or really integrating the equations of motion and use it to compute the velocity fields. There is no much difference. Well, we can argue. I mean, you can find details, you can sort of slice through different positions, different opinions, and see pros and cons. So somebody may not fully agree on what I'm saying, but I'm trying to say that in a statistical ensemble, anyway, you have to average. That's all I'm saying. So where does it make sense to use velocity? And when does it make sense to use it? Well, sorry, when it does make sense to use a field, and when does it make sense to retain the particle position? And I think the matter of everything is fluctuations. So let's take an extreme case where we all agree field formulation is not probably the best formulation you can possibly take. Suppose you have a particle. I don't know. Suppose you have a very sparse system. And maybe you want to study the pathways through which, this sparse system goes through some kind of a topological constraint to reach another part. Just making up a problem as I'm speaking. If you want to study the dynamics of this system by integrating out the equations of motion of these few particles, well, you get what? I don't know. Let's say this is, for sake of simplicity, a two-dimensional system. Then you get 2, 4, 6, 8 times 2 variables in phase space, 16 variables. So by integrating equations of motion and following the dynamics of 16 variables, you're done. And then, of course, you have to do it many, many times. On the other hand, you might choose to use a field theory representation and do a Monte Carlo over the value of the density of the particle in a grid. Now, clearly, then you probably have a Monte Carlo that defines the average density of fields, and then you average over this field. How can you do it? Well, trivially, suppose you're interested in the Boltzmann distribution. The Boltzmann distribution is the integral over x of e to the minus beta u of x. This is the macro vector. And you might introduce, we'll see how this can be done, a functional over a density and then say that your density is nothing but, a density. You're basically saying that the density is a density, so that the density fields here is basically a sum of delta function of all the particles, e to the minus beta h of x, right? And then you can reverse this and say, okay, now I take this integral on this side, and if you can manipulate this equation, you might come to a conclusion that you can rewrite this in the following way. This is a function over the configuration of a field. Notice that I use functional integral now because, well, I'll explain in a moment what this is. So let me put a question mark. Then I have, say, some function g, which is a function of the field. And e to the minus g of the field is defined as the integral over dx of e to the minus beta x times rho x minus sum over I x delta of x minus xi. Now this delta function now tells me basically that the density field is the density of particle at point x. Right? Now this is telling me that basically what this equation here is doing is rewriting the partition function in terms of a density, in terms of fields. And what this integral is really, this integral is really a product of integrals, which 1, 2, 3, and this is the value of the density in each point of the grid. 1, 2, 3, and you have to integrate over all possible values of the density. And in each of these points here, the value corresponds to the average density of particle in that point. Right? So this discussion is basically telling me that I can represent the same thermodynamical system through a particle representation or a field representation. So let me write it again just for sake of clarity. I could write the partition function for the system as in particle representation, still working in configuration space for simplicity. You can do it in phase space if you want. Or you can write it in field representation, where now this is an integral over fields, and this symbol means I'm integrating over the value of the fields in each point of a grid. And then I take the number of grid points as large as I need, times an effective interactions, effective Hamiltonian for the fields, that is a functional of the field, because it depends on the value of the field in each point in the grid. And this effective functional implicitly comes from the microscopic picture through the integral that we did before. So now I'm not copying this. So basically, in going from here to here, I've inserted an integral over fields, and I've taken out with as many delta functions as I have positions, as I have values of fields in different positions. So that's called a delta functional, which is basically a product of delta function, one for each value of rho in each point of the grid. And I've reshuffled all the microscopic information into the probability of a given field configurations. So in principle, these are two completely equivalent ways of writing, from a formal perspective, the same partition function. One in terms of particles, and this x is really a product of this macro x is really a collection of atomic coordinates, right? So it's like x1 to xn. Or I can use density fields. That's an example, right? So let me go back to the question. When is it beneficial to go and use density fields? Here is our problem we used before, and we assume we have 4 particles. Now you see, if you want to define density fields, a very crude way of going around the question, what is better, fields or particles, is how much effort do I need to do to describe it in terms of fields or in terms of particles? Well, if I suppose I want to take a field representation, then how many lattice points do I need to define? How fine needs the grid to be for my field to be representative of a physical system? So here is the grid where I define my fields. And remember, functional integral of free fields is basically the limit of taking as many of these grids as I need. And remember, I stop when the resolution that I achieve is in a gap and it's well above the resolution of my experiment. That's the effective approach, right? Effective theory approach. Now, as usual, the size of the grid depends on the size of the dynamics I'm interested in resolving. For instance, it is clear that I cannot take as grid size something like this, because you see the essential dynamics that is crucial for this process occurs, which is for instance the passing through this hole, occurs at a much lower length scale. So if I was gridding my problem with very fine grain, coarse grained grids, I would miss important physics that occurs at a short time scale in a scale that within the grid. So the lattice spacing once again is the UV cutoff resolution, and I want my UV cutoff resolution to be much lower than the shortest length scale that is relevant for the physics of my problem. So in this case, clearly my lattice must be much smaller than this. It is open, so say, just to design something like this. Probably something like this is the kind of grid that I would really need. Now, it is quite likely that if I'm forced to use this grid, the number of degrees of freedom in my problem, that is the value of the field in any of these grid points, because those are the variables in my partition function, very quickly exceed the 16 numbers of degrees of freedom I had for 4 particles. Maybe you have to introduce hundreds of thousands or hundreds of lattice points rather than just 16. So when you want to solve this problem, you begin to think that maybe fields is not the right reason. So this is the mathematical or computational perspective. The physical perspective is that these fields oscillate dramatically configuration by configuration, because it's a delta function here. If you have only 4 particles, the average density are huge delta functions here, huge delta functions here, huge delta functions here, and there was another one here, I don't know. And then basically 0 everywhere else. So every field configuration is radically different from one another. The field is widely fluctuating within space. So that means that when you want to achieve a convergent average of widely fluctuating objects, you have to average over very, very many configurations. And the result is that, widely fluctuating ensembles are not suitable for physical descriptions. In the extreme case in which you have 1 particle, you see what I mean. You have basically all grids variable except one are carrying physical information, but you have to somehow an average over all of them. So this is an extremely fluctuating ensemble, configuration by configuration, and this is clearly not a good approach to study and physically formulate this physical system. So really, the question of the field is a question of how many degrees of freedom you want to average, and basically fields become the option whenever within the typical length scale where you place your cutoff, there are always relatively large number of particles. Because you see, then the central limit theorem comes at your help, and will tell you that the field will be weakly fluctuating over space, because in each point of the grid there will be a density that is averaged over a large number of numbers, and on average this will be leveled out throughout the system. So let me say it again, and I'm just repeating the same concept twice, but it's an essential concept when you start describing field theory. Fields becomes an option anytime at the desired level of resolution you need to take, which is dictated by the physical system you're considering, the number of effective grid cells you need to introduce to define the field in a meaningful manner is sufficiently large to include, on average, many particles, or many microscopic degrees of freedom. Because if you do that, then you won't be in a situation in which your field is zero everywhere except in a couple of points, and therefore fluctuations are dominating. You will be instead in the opposite scenario, dominated by the central limit theorem, where the field will be weakly fluctuating in space. So fields are a tool to get a simplified, meaningful description, while at a conceptual level in statistical physics there isn't much difference between the two, because in both cases you're forced to be making averages. So I think these descriptions clearly illustrate how fields are deeply intertwined with the concept of effective theory. Effective theory breeds fields as a possible natural outcome, because effective theory breeds the concept of effective resolution and cutoff scale, and fields may become beneficial description of the same physical system in effective theory descriptions where you're only interested in the physics below that cutoff scale. Okay, so I hope I came along with you with convincing you what is the size for doing, what is the advantage of doing fields. I want to open a parenthesis that is for mostly theoretical physicist oriented, high energy physics oriented people in the audience. In quantum mechanics, you typically use fields in quantum many-body problems. You use fields very much following the same reasoning that I just mentioned in statistical mechanics. You use second quantization for electrons in condensed matter when you have electrons distributed, many electrons propagating through, say, a conductor or whatever semiconductor, and it makes very much sense to talk about density of electrons rather than individual electrons in quantum mechanics, right? That's the natural description. In relativistic quantum field theory, fields are really playing the same role, and so, but normally in fields, in relativistic quantum field theory, very often we concern only scattering problems. And when you have a scattering problem, typically, you would probably naively think you have just a couple of degrees of freedom, the target and the scattering particle. But actually, this is not really true, because relativistic quantum mechanics is in fact an infinite dimensional theory, meaning that since the number of particles is not conserved, you are supposed to sum over infinitely many possible particles, which corresponds to processes in which you create particle or absorb particle. So in a relativistic framework, you could view the urge of using field theory in relativistic quantum mechanics in the perspective that in relativistic quantum mechanics, there can be any number of particles. Therefore, I'm always in a situation where I cannot go along with a finite number of them. So I mean in extreme large number of particle case, if you want to build an analogy with the discussion that I've been doing to this point. Okay, having gone through this very broad and wordy introduction, let me try now to narrow up our discussion. And I will do that by considering a specific example as a prototypical example. So throughout the rest of this course, I will consider spin fields or magnetization fields. So, but we'll see later, maybe, if time allows, that is exactly an identical mathematical formulation can be used in polymer field theory, and now your density will be the density of polymers in a melt, or in. So the fact that I refer to spin fields is 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 not specifically because we are interested in spin fields, but because this is a prototypical toy model to introduce fields. And as soon as you get practice on that, you discover that you see fields everywhere in physical problem if you want. So our sort of reference idea would be the Ising model, which is a sort of a obsessions for physicists, or if you want, the analog Landau theory for those who have taken statistical mechanics advanced or some of the other statistical mechanics models. So if you want, we imagine to work in a lattice. Now the lattice has a real physical meaning in this case, but you can think about it as the finest possible lattice. You can build this one that really corresponds to the physical lattice of your chunk of metal. And in each side of this lattice, you might put a spin variable. And in the Ising model specifically, spins can be plus and minus some number, 1 or 1/2, if we want to think in terms of statistical mechanics, which reflects some intrinsic quantum behavior, but there's an open discussion whether the Ising model, to what extent the Ising model is really quantum, or how much quantum is the Ising model. I will skip all that because this is not a course on the Ising model. Okay. And then, for instance, you can get a nearest neighbor type of interactions with this SI, SJ, nearest neighbor coupling, which tries to account for the magnetic interaction between these fields. So let me remind you, what is the Ising Hamiltonian? The Ising Hamiltonian is the sum of our nearest neighbor I and j, Si, Sj with a negative sign and a coupling. Let me call the coupling J maybe. And you might complicate this model at your taste, for instance, considering generalized Ising models in which J's are different from side to side. These are called spin glass systems, whatever. I don't really care about what kind of Ising model one wants to look at this level, because the discussion is more general than that. And you might add a source term, or we see why we call it a source term, but you might add an interaction with an external magnetic field. So let's call it mu p k s k. And each s can take plus minus 1/2. So your partition function is the sum over all the s1 equal plus 1/2, s2 equals 1/2 plus minus, and blah 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 blah. You have a discrete sum over the value of the spin in each value of the grid, each of which can take values plus and minus 1, and then you have e to the minus beta and your Hamiltonian, which is a function of all this spin. Now, I know you know this. I'm just setting the stage. Now we see how you can make a transition from this microscopic point of view. In this case, the individual spin are really the analog of particles in the examples in the examples I was mentioning before, and fields. And the idea is to do what I said in words we would have done, to consider blocks, chunks of this lattice, and associate to this point a new variable. Let me use a different color. Call it phi k. Let me use another label. And phi k is really the average over the size of a typical block. Let's suppose n are in this case are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, blah, blah, blah. Right, this is the number of lattice points in the block of the spin. Now, if you look at this spin, well, now you can actually discover that phi can take a discrete set of values from a maximum to its negative maximum at discrete jumps, just as much as angular momentum sums in quantum mechanics, right? Because if I align all the spins to be up, then phi max is, I don't know, 1/2, right? Where all the spins are up, and then I sum over all them and divide it by the number of spins in the chunk, and find a negative phi 1 is -1/2. And then I have n 2n minus 1. Is that possible? Discrete values of that. So it looks like we went from a discrete description to another discrete description. This is called Kadanoff blocking, by the way. We'll come back to that if we describe a renormalization group flow at some point at the end of the course. Still depends how far we go on this field theory introduction. Kadanoff blocking will sort of go from one discrete version to another discrete version. But now suppose that the cutoff of my theory, the famous 102 pi over lambda, where lambda is a frequency that I'm interested in, is such that I'm interested in dynamics at distances much smaller, much larger than the lattice space. Then effectively this corresponds to sending n to infinity. Now if you send n to infinity, two things happen. In the limit in which n goes to infinity, I have to move my face from here to show it, two things happen. First, the phi k becomes continuous, or let's say rather than continuous, it becomes dense in values, means that delta phi in the quantization of phi from the maximum to the minimum, which is the negative maximum value, the jumps are cut down by 1 over n, so they become very, very, very dense. That is equivalent to the classical limit of quantized systems. But also the variable phi of k becomes a phi of x, because, you know, I can define it on a grid and assign a point x, and this point is representative to a neighborhood that is arbitrarily small with respect to the size of the system. So I can replace with a continuous field over a continuous variable, if I want. The second reason, the second emergent phenomena that is setting in when the number of field variables goes, when the number of implicit average in the Kadanoff blocking goes to infinity, is that typically typical values of phi's are close to 0. The reason is the central limit theorem, right? When you average over many, many, many particles, you get you average over many, many random variable, and the result of that is that normally in paramagnetic conditions, if you are in ferromagnetic conditions, situations may change, and that's why you can only work very close to the phase transition, where you just live in the paramagnetic phase. But let me not go into the detail of non-Dow theory, but typically for situations where you're allowed to use fields, your field values are typically small. So which means that I can replace the integral from minus, say, phi max to phi max of a function that is much concentrated, much focused. This is phi negative phi max, this is phi max, and this is the typical Gaussian that for values for phi that come from central limit theorem. Now you see the typical sigma of this Gaussian is much smaller, so doing the integral from minus phi max to 2 max or doing the integral from minus infinity to plus infinity is essentially the same thing. So basically, rather than having to sum now over infinitely many spin and sum over 1/2 of spins, now you can form a functional integral over the fields where each of the integrals inside the fields goes from minus infinity to plus infinity. Any of you who has done calculus 2 knows that computing integral is so much simpler than computing sum, discrete sums. There are just a handful of sums that can be, series that can be summed exactly, while there is a plethora of integrals that can be integrated analytically. And in particular, Gaussian integrals can be done analytically, but Gaussian series are not something you want to do. Typically, to compute series, you have to define integrals where you have over complex functions with infinitely many poles, and then you do the integrals over the complex functions using residues theorem to get the sum over the poles. So you can already imagine how cumbersome this mathematical construction is and how difficult it is in general to arrive to such a conclusion. So you maybe see that this idea of using continuous fields defined over a continuous variable can become handy when you want to do calculations in so simplified case. Now the last thing we want to say is, how does the Hamiltonian for the fields look like? And here comes the strength of the effective field theory approach that we discovered at the beginning of this course, in the part of the course that unfortunately is not on the YouTube channel, because this was the part that we gave live at the beginning of the course. If I'll have time at the end of the course, I will re-record also that part. But nevertheless, let's not focus on that, and let's go straight on what I wanted to say. Look, let me start with a consideration. Suppose I have my fields now, my scalar fields phi, which describes the local magnetization or spin density, to be more accurate, of my fields. Now, we know that the underlying theory has interactions between spins, therefore this brings in correlations. And correlations between, say, the value here and the value here will try, if this is a magnetic correlation, for instance, it will try to maintain the same value of the field across two cells, right? So how can I mathematically do this? Well, in principle, I can say, I can get terms in which I evaluate the value of the field x and I multiply the value of the x plus a lattice, macroscopic lattice difference, which is basically delta x, right? And put some magnetic interaction. Now, when you do this across your lattice, where you define the fields, and in addition to this, you will also get the price for you know, getting a high value of the field here is obviously a rare event. Because it needs all the magnets to align in one direction. So you will get some energetic cost or gain of having powers of value of the field in a single point. Yeah. So what happens? If you look at these two terms and if you combine them, you discover that what you generate is second derivatives. Why? Because if I take, say, what is the phi, for instance, now that's considering this phi, and then I will do phi of phi I plus 1, plus phi I minus 1, negative 2 phi of I squared, so 2 negative phi of I, divided by 2 lattice space, right? Now you see that from these couplings, essentially, and these couplings generate derivatives of the fields. So everything that we said is that I expect if the field is interacting, meaning if it can feel its values and because of interaction it can sort of explore at least a neighborhood, I will quickly generate polynomial interaction terms and I will quickly generate derivative interaction terms. Of course, if I have a higher derivative, say here rather than second derivative, fourth derivative, then of course this will include interaction between I plus 4, I plus 3, it's a higher and higher number because you need more and more points to define higher order derivatives, which means basically that the more local, the more long-ranged are the interactions, the higher number of derivatives they will basically generate in the effective theory for fields. So, with all this in hand, we can now use the effective field theory formalism and remember the recipe for constructing rigorous effective theory. And the recipe, which was stated by the normalization group-based effective field theory, now I added a field to specifically refer to theories for fields, and is consider if you have any well-known infrared physics, bring it in. And whatever is the ultraviolet physics, you can build as a sum of local terms, potentially depending on derivatives, and from the most general combination that is compatible with the symmetries. So my Hamiltonian will be, in general, a combination of terms of the type, say, C naught phi square of x plus C, well, I could in principle say, let's say, C1 phi 1 plus C2 phi 2 square phi square, sorry. This is a function of x. This is a sine integral over x. Then I have a C3 phi cube of x and blah, 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 blah. Okay? And then I have also terms like phi grad square phi. Then I have plus term, I don't know, phi grad square phi, square here, or I might have, I don't know, phi grad 4 phi. Some of these terms are redundant because I can go from one another by applying integration by part. So all I do is basically renormalize the coefficients. So this is D2, D21, I don't know, D4, whatever you want to call it. So sometimes you can go for instance, this term here is basically the same as the term d phi, because the two are related by integration by part. So, I don't need to include both of them because one can go from one to the other. So all I'm saying now is that Hamiltonian in principle contains all these counterterms. Remember the concept of counterterms with unknown coefficients, each of which is principle there. Is in principle there. So now, as usual, if you have a Hamiltonian with infinitely many terms, you need infinitely many constants. Each constant will require an experiment to be fixed or microscopic calculations, and you can never do infinite experiments or infinitely many calculations. So unless you can cut this series down, this is a useless expression. Is not a physical theory. It's just a way of counting possible combination of polynomials and derivatives of fields. It does not represent a physical theory. The only way you can make this a physical theory is to stop the series. And how do you stop this series? How do you choose which terms to account for and which terms you want to drop off? Now, here comes the usual dilemma that we discussed at the beginning of this course. This is the choice you have to make between making a model and making an effective theory. If you want to make a phenomenological model, choose whatever you want, you learn something. Just as much as when we started off with a delta function as some approximation for the short-range interaction in the exercise we used on the Schrödinger equation. It was a purely phenomenological model. It taught us that there was some distance physics, some short distance physics. So it was a useful model, but it was not at all trying to be any rigorous. But then we did things a little bit more elaborately, and we convinced ourselves that there was a way of doing a power counting in organizing all the correction in a systematic way, with in mind that we were retaining those that dominate in the long distance regime first, and then adding new terms if we want to get more and more accuracy. And these new terms will become relevant only when the resolution will approach the cutoff, just as much as we need more and more multiple terms if we get closer and closer and closer to the charge distribution of electrostatics. I'm going fast on this part because we've discussed this, and if you haven't taken those lectures, read Lepage lectures of renormalizing the Schrödinger equation you can find in the webpage of my course in the University of Trento. So, we need a power counting rule. We need a rule, a recipe to decide which terms in this long terms expression should not be accounted for. Now, two observations. Observation number one, phi of n plus 1 will provide effect smaller than phi of n. Polynomial, higher order polynomial will be less relevant in the interaction. Why? Because remember, the values of the fields in the regime where field theory is applicable are small. So that's why all the Hamiltonians we ever considered, almost, some exceptions, but in textbooks, most of the time, if the textbook is not Itzkinson-Zuber or, I don't know, one of these huge manuals for quantum theory that contains basically everything that has been done until the point that we're published in quantitative theory, in normal textbooks, you see that all physical theories you look at are polynomial in fields, right, with some derivatives. They correspond effectively to the Taylor expansion of a known Hamiltonian, truncated up to a point. Because we assume fields are few. And, okay, I will skip for the moment the quantum field theory interpretation of large polynomial, but those of you who have some background in quantum field theory, they know that the higher is the polynomial of the interaction, the more body are involved in the vertex. So 5 to the 6 is a 3-body interaction, just to say one. 5 to the 8th is a 4-body interaction, and so on and so forth. So if the density is low, the occurrence of simultaneous 4-body interactions is small compared to the occurrence of 2 3-body interactions. Okay. The second important rule that you need to account for when you define Seville theory is that derivatives don't matter at low energy. In fact, when you have a term, say when you have a term with a derivative, well, when you go to momentum space, this will come up with a factor k2. k squared, because remember in momentum space derivatives become factors of lattice momentum. Now at low energies you are only sensitive to low momentum, long wavelengths. So long wavelengths change very weakly, so this is small, or carry low momentum on a lattice. The momentum, you know, is just a conjugate lattice, the reciprocal lattice. But so there is this Umklapp mechanism. I don't want to go into that too much, but anyway, it's an energy scale. It's associated with an energy scale through dispersion relationships. So basically, as long as you have a cutoff with a certain resolution power, and you're interested in dynamics at very long wavelengths, very very low resolution dynamics, then the least order of the derivative are those that matters the most. So, for instance, with this in mind, I am almost done in defining a low energy Hamiltonian for my fields without having to model any particular specific model for the microscopic dynamics. I don't even have to know that is an Ising model or not. It's some kind of short-range interaction between the spin. And this will include terms like phi, quadratic term first. So the lowest term will be one I use in notation borrowed from quantum field theory using a parameter. I would call it m. But of course, I can use any other number. I can also have a term with this value here. Now it's which corresponds to shorter scale interaction, so correlation between fields at different values, and it's still quadratic. Then let's go further. I could have higher order terms here, but these I cancel out. Well, I can include it, but you know there would be subleading in the AFT framework with respect to this kind of derivative terms. And of course, I can include higher order potential, like phi to the cube. So let's call it this lambda 303. For technical reason, they will become clear later along the course. I put a factorial here, it's just a redefinition of the parameter lambda. I could put also quadratic terms, lambda 4 over 4 factorials. And of course, I could put any combination of cubic and derivative, but they will, again, lead to higher order corrections. Now, the only thing that I'm left to specify is whether how much does it cost to add one more derivative relative to add one more power of field. And this defines my personal power counting. That's the last freedom I'm left with that is not completely specified by these articles. And this is where you're pushing your model dependency in a corner, which defines what's the power counting scheme you want to use. For instance, you might decide that one derivative is worth twice powers of the fields, which will tell you to include certain number of derivatives and certain number of powers. Or you might decide on the scheme, so you will have still the least number of derivatives and you'd rather pay adding more powers of fields. Or you might decide that they are worth equal and then you get another Hamiltonian. So typically this choice of power counting scheme only affects the last terms you keep, and therefore only becomes important when you approach the cutoff. For the very, very ultra infrared physics, it doesn't really matter. So it only affects how convergent is your effective theory, so to say. So in particular, with all this in mind, we come out that in this specific case, a very decent theory to consider is one that has this structure. Now, notice that I excluded odd powers of fields. Why odd power of fields? Because I'm assuming that unless I act from the exterior with some force, then clearly the system is invariant under reflection over the z-axis. So if I put an odd power of fields, then that would flip sign whether I flip the axis, right? And that is a symmetry of the system we think is protecting from this to happen. We think that the magnet spontaneous magnet that sticks on your bridge, on your fridge, doesn't change if I flip it upside down, right? On the other hand, if I have an external magnetic field, then of course you get a compass, and it does matter whether it's in one direction or in the other. So typically, what you have an even number of power, and then when you add external sources of interaction, such as an external magnetic field, you might get odd terms. For instance, you might get an interaction with an external magnetic field. Of course, you might get also interactions which corresponds to higher powers. But then again, you assume that if you assume that interaction with the external fields are weak, you can neglect this. This is part of your powers quantity. So all this construction is to say that in the rest of this course, we will focus on Hamiltonian like this. Occasionally, we might consider something different. I'm not saying this is not the only field theory there is in the world, but I'm just saying how a very nature of field theory structure that is the same that happens in the famous applications of quantum field theory, by the way, enters naturally in statistical mechanics if you apply renormalization group arguments to a system, for instance, to a system of spins.